All right, so we're going to start with number 7 here, and that would be a momentum before and after type of problem. All right, so we've got this canoeist stands in the middle of the canoe, initially are at rest, and the canoe is pointed towards the shore. Towards what I would see this. All right. And they say speed, so I don't really have to worry about direction. And they want to know something about mass, and then if it increased it. All right, so I don't think I really need to write anything. I could write that what's right there? Person and canoe are a system. You know, the slickness of the canoe on the water means that it's separate from the water. You know, low friction. If it was high friction, then that wouldn't be true. So, beforehand, let's see. Now, if you can't draw your canoe as well as I do, don't feel bad. But that would be my before, right? They're both just sitting there. During would be her starting to walk. And I'm going to have her walk to the left, which means she has to put an impulse on the canoe. So impulse on the canoe by the person would go that way, so that the impulse on the person by the canoe would go in the direction she's going to end up moving. Remember, impulses are always equal and opposite. They're always on opposite bodies. That's why when we take time out of them, we get Newton's third law. Right? But they are what creates Newton's third law. And then the afterwards is going to be that the canoe has momentum this way, and she has, excuse me, momentum that way. Any questions? Anything I can clarify? Yeah. That way. I put it to the left. Could you put it to the right? Sure. But it does bring us, which way do we want to define as positive? So left? I think that's a good idea. So in all of these diagrams, we'll put positive to the left. Any other question on the why before we move to the how? Alrighty, let's see. On the how, I need to start with a valid physics equation. Maybe I'll throw momentum up there. Inertia times velocity. And then I'm going to start with the fact that momentum is conserved. So momentum of the system, this is also from our equation sheet, before equals the momentum of the system after.
What does the apostrophe mean?
That means it's actually called a prime mark. It just means another value of the same thing.
Okay.
Commonly, because we're dealing with momentum of 1, momentum of 2, momentum of the, we use the primes to indicate before and after. No prime before, prime after, double prime, another different value.
Yeah.
In calculus, you do it for different functions. Good? Good start? Okay. So let's see, what was the momentum of the system beforehand? So I can go back up to my diagram. How much momentum did I draw beforehand? None. So what's the momentum of the system? 0. Oh, it's like doing the diagram helped me solve it? Weird. And then afterwards, let's see, we had the momentum of the person, and that was positive, and then a negative momentum of the canoe. How did I know the momentum of the canoe was negative from my diagram? Points in the negative direction, right? Oh. So the momentum of the person equals the momentum of the canoe. Inertia of the person, velocity of the person. Actually, we already took care of it. It should be speed in there. Inertia of the canoe, speed of the canoe. Because I took care of the vector part down here. These should have had vector symbols. And I took apart the direct. Oh, now I can just plug in, right? Let's see. 6332. 63 kilograms. Moving at 0.95. .32 kilograms. Speed of the canoe. And I got 1.87 meters per second, which makes sense. Their momentums have to be the same, and if I have a lower inertia, that means I'd have a higher speed. Yay! And then, of course, you can do I'm pretty sure if you can do part A with me, you can do parts B and C on your own. Alright, so we're going on to the ever-popular number one. And with the new masses, and they're moving and things like that. So we're going to use an energy bar graph. And I'm going to actually, I'm going to draw 2 bars for each thing. Because I've got mass 1, I've got mass 2. Alright, so I've got 2 things in my system. I think there's going to be some potential energy grab going on here. Alright? And so let's see. Mass 1. One I'm going to do in blue. At this initial position, it has some gravitational potential energy. I'm going to set my 0 point where my block hits, my M2 hits the ground, just before it hits the ground. So that means the position is different for M1 and M2 now, so they're going to have some gravitational potential energy at the beginning. So I'm going to, let's give this one 4 bars worth. That's my M1. My M2, it's bigger, so let's give it a little bit more. Actually, I'm going to give it 6. Alright? It's more massive, therefore it's on the same height, it has more gravitational potential energy because its mg is bigger.
Are we measuring the height of the center of mass?
Yes. Always deal with center of mass, because remember, until we talk about rotational inertia and some other factors, you would really like to consider everything to be a particle. But it gets kind of weird to say the particle is attached to the end of the particle thin rope. At the other end, there's a different particle. It gets boring. Even more. The mass is attached to the rope. Anyone figure out if the 2 things are moving, they're connected by a rope that stays tight? What can we know about their motion? Huh? You're brilliant. You're right. They have to be moving at the same speed. Right? Think about it for a minute. What would happen if the person in front moved slower? What would happen to the rope? Anybody? Try it sometime. Get a friend. tie a rope to each other. No, hold a rope between you and try running. See what happens. It'll be a fun afternoon. Watch out for trees and dogs.
I don't watch it.
Then it'll be even a funner afternoon. It might involve new friends who wear scrubs. All right. I think I'm good for before. Afterwards, they're both going to be moving. So what type of energy are they going to have? Kinetic energy. Now, I'm going to have zero potential grab because of the location of M2 for M2, but M1 is not in that location, so it's not going to have zero potential energy grab. So let's see. So they're going to be moving. So I don't think they're going to be moving very fast, so I'm going to say M1 only has 2 blocks here, but M2 has more inertia, so it's going to have a little bit more, but M1 is going to be at a different location, so it's going to have some potential energy graph, and it's at a higher location than it was before, so it has to have more. Let's see if I did it right. Let's see, 1, 2, 3, 4 plus 6 is 10. Ah, and I add up 10 and 10, which means energy is conserved, which is kind of good because it has to be, right? Yeah.
Also, theoretical question, but
Sure.
if you had a system that was so big that you could see the curvature of the Earth, would the point that we made the potential energy for gravity 0 as well?
Yep. Because everything flat on our curved Earth is actually a curve.
What if
There was a fizz about that,
there was?
about the tops of a bridge being further apart
yeah.
than the bottoms because of the curvature of the Earth. Really long bridge.
And so, if you had a system that somehow went below the 0 point and went through the center of the Earth and out the other way, would that mean that there are 2 parallel points of 0, even though they're on a
Yep.
curved line if you had that section of the system?
Yes. Yep. Good thought. All right. Now my equation for my how comes directly from this, right? So I'm going to have 5 terms. Let's see, I'll color code them. So we have PE of 1 plus, keep me on track because it is Monday morning, PE of 2, and that equals KE of 1 plus KE of 2 plus PE of 1, but a different value, so I'm going to put a prime on it. And those come right from my bars, right? All right, so M1G. Now I'm going to call the height I'm going to call this point where M2 ends up as 0. That means M1 and M2 start at a height of h, right? And M1 ends up at a height of 2h. Yes? Does that make sense? Okay. So h plus M2G, h equals 1/2 M1V squared. And I can just use V because there's only one speed, right? They're both moving at the same speed. Why are they moving? Why do we know they're moving at the same speed? Because they're connected by the rope, which makes them one body. Plus 1/2 M2V squared plus M1G times 2H. And I probably should have started off, right, with Good old valid equation. Sorry, I'm not doing a good job modeling. Now they want me to solve for v. They want to know speed. So, try some algebra magic. See if you can get v by itself. There are. The m's are not going to cancel out. You're going to be left with m's, g's, and h's. So, let's see. Here was my intermediate step. Well, I pulled everything that had any type of M, a G, and an H into it on the left side. And I kept anything that had any type of M, a 1/2 and a V in it on the right side. And then I factored out common terms. I brought it over the other side, which made it negative 2H. Well, M1, negative M1G, yes, because there's an M1GH over there and an M1G2H over here, so when I bring the 2H over there, it becomes negative, and 1 plus negative 2 is negative 1.
So would a question like this be on the next thing?
It could be, yeah. I mean, because it's just conservation of energy. You could also put the green equation, or the blue equation here with all the terms, into Wolfram. And
use Wolfram on quizzes?
yeah, and tell it to solve for V. So. But it is really, you group like terms on one side and then just factor out common parts. And I think part B of this question just asks you to use that factor to check it, make sure it comes out correctly. All right, so we're going on to number 9 here, where you have a geological hammer and a rock, and their collision we're going to assume is elastic. So right away, as soon as I hear elastic collision, I think, oh, boom. Momentum is conserved, but so is kinetic energy. That's what it means by elastic, right? If it's semi-elastic, inelastic, any of those, that's not true. Only momentum is conserved. So I go over here, number 9. Before, I just have my hammer and my rock. Yay!
A couple of dots in the rock.
Yes, sir. During hammer hits rock, Impulse on rock by hammer. Impulse on hammer by rock. Afterwards, actually, whoops, I messed this one up. Momentum of hammer, I would say. Otherwise, they're never going to hit, but you would swing the hammer, right? They tell me anything about, let's see what they tell me. All right, that's all they tell me. But they tell me 0.2 kilogram rock hammer, or 0.2 kilogram rock and a 0.55 kilogram hammer. So I think if the hammer is heavier, after it hits the rock, it's going to continue moving forward. If it was lighter, I would think it'd move backwards. If it was the same mass, I think it would stop and the other one would move. But that's just kind of, the nice thing is if I screw up, it'll tell me by giving me negative answers when I don't predict negative answers. Momentum of the rock. Momentum of the hammer, but afterwards. Good? Now, if you look at the rubric, which you should, there is an exit ticket to do, folks, which I think has come live. So, if you find yourself in a couple extra minutes, do the exit ticket before class ends. I'll try to work fast here. Momentum is mass velocity, kinetic energy, inertia, speed. Oops. From the equation sheet also, momentum of the system before equals momentum of the system afterwards. And also, because it's elastic, kinetic energy of the system before equals the kinetic energy of the system afterwards. Right? That's because it's elastic. So beforehand, I had the momentum of the hammer. Afterwards, I had the momentum of the hammer prime plus the momentum of the rock. Same for kinetic energy. Now, if it makes you more comfortable, you could do everything afterwards with little primes, if that makes more sense to you. I'm being lazy. Actually, I should put the primes on there. But that means I have to go back up here and put a prime there. And now it's substituting in inertia of the hammer, velocity of the hammer, equals inertia of the hammer, velocity of the hammer afterwards, plus inertia of the rock, velocity of the rock afterwards, 1/2 inertia of the hammer, speed of the hammer, 1/2 inertia of the hammer, velocity of the hammer afterwards. And the reason I've done these two next to each other is because at this point, after I would do all my substitution, I can't go any further unless I solve both equations together. Or algebraically, whatever algebra tricks I need to do. Personally, I use Wolfram. My next step is going to be to substitute in, and then after that, it would just be me putting it into Wolfram so it can solve the two simultaneously. So let's see. Substituting in 0.2, 0.55. kilograms. Velocity of the hammer is 5.2. And then now it's just algebra, right? Oh, algebra, my old friend. We've come to meet again.